So far, we've worked with the major pieces of the confidence interval and we put them together or take them apart so that we can see how the confidence intervals are built, right? We talked about the point estimate and the margin of error, the upper and lower bounds, and how we write out our interpretation. But let's back up a little bit for a second and let's say we're still in the planning phase of a study. And let's say we want to guarantee a specific margin of error or maintain a certain confidence level. We need to know how many people or how many members to put in our sample. And that's where sample size calculations come in, which is what we're going to talk about in the last few examples. So I haven't brought this up yet, but I'll write it out now. If we were calculating the error on our own without looking at a confidence interval that's already built, okay, the formula for that is that the error is equal to our z critical, which I'll talk about that in just a minute, times our standard deviation divided by the square root of n, which is our sample size. This is our error formula. So this formula shows that there's a relationship between these important values, the margin of error, the critical value, which is highly connected to our confidence level. Let me put that in here. This is directly related to our confidence level. And like I said, I'll get into that in just a minute. We have our population standard deviation and our sample size. These are all related when we're dealing with confidence intervals. And these play a very critical role on how precise our estimate is. So, for example, if we have a larger standard deviation, that means there's more variability, so we need a larger sample to keep the error small. If we have a higher confidence level, this leads to a larger critical value, which increases the margin of error unless we increase the sample size. And if we want a smaller error, we need to increase the sample size. These are all connected. Now, this formula here for the error, if I just rearrange that formula and solve it for n, that's where we get this formula. These two are the same exact formula, just one's rearranged for n and the other is rearranged for e. So this is where our sample size formula comes in for the means. When we're dealing with means, this is the sample size formula we want to use. Now, if we're dealing with proportions, we want to use this formula here. These two formulas are exactly the same. They look different, but this one below is just a special case. If we don't know what our value of P is, which is our preliminary estimate based on previous studies, then we estimate P to be 0.5. So when we put in 0.5 for both of these P's, that's where this 1/4 comes in, because I would have 0.5 times 0.5, which is 0.25 or 1/4. So these formulas are the same. It's just that formula number 3 down here is just a special case of number 2. Now I'm going to talk to you about what a z-critical value is, what it means, and how we can find it, because we're going to need that for our sample size formula. A z-critical value tells us how far away that we're coming out from the center to create our interval in terms of standard deviations. So that's why we're calling it a z-critical, because we're using z-scores. So a z-critical is a z-score. It tells us how far out from the center we are coming out to create our interval in terms of standard deviations. And now how far we come out depends on the confidence level. If we want a higher confidence level, that means there's going to be more area under the curve and the interval is going to be wider. So that means the z-critical is going to come out further in either direction. So I have two examples here. In this example with the purple shaded area, this is an example of a 90% confidence interval. 90% falls between these two cutoff values. Okay, so that's all the shaded areas, that 90%. Now, if we want to find our Z critical, we need to know how far out we're coming out to this cutoff point and how far out we're coming out to this cutoff point. And that is solely relying on the confidence level. If you look over here, if it's a 95% confidence level, see, we come out further. So our Z value or our Z critical value will be bigger because we're coming out further from the center. Now, to find the Z critical value, we want to use the standard normal curve because we're talking about Z-scores. We're talking about the number of standard deviations away from the center. If I have a 90% confidence interval, that means 90% of the area is going to be in the middle. So that means there's 10% left over. And then if we split that between the two wings, we get 5% in each of these two wings. In decimal form, it would be 0.05. So let's go and view our probability calculator. I'm going to remove my algebra and graphics since we don't need that. All right, we want to be on the normal distribution. And since we're doing a standardized curve, working with our Z's, our mean and standard deviation should be 0 and 1. Whenever you're dealing with Z's, you want to make sure that the mean is 0 and the standard deviation is 1. Now, if we have a 90% confidence interval, that means 90% should be in the middle and 0.05 should be in each wing. So to find how far out we're coming from the center out in terms of standard deviations, I want to find that cutoff point for 0.05. So I'm going to choose my left wing so that it's shaded to the left, and I want to put in 0.05 because that's how much I want shaded in that wing. So on the left side, this cutoff point would be that I come out if we round it to two places, I come out 1.64 to the left, 1.64 standard deviations for this cutoff point. Now that's going to give me the same exact thing on the other side because of symmetry, it's just going to be positive instead. Let's check. So if I look at the right-hand wing, so I'm going to choose right hand, I'm going to put in 0.05. And see, I get the same thing. It's just on the positive side. Zero's in the center, and then this tells me how many standard deviations to come out this way. So my Z critical for a 90% confidence interval is 1.64 when we round it to two places, because that's how far I need to come out in either direction from the center in terms of standard deviations. Now, if I do, let's practice and do it for the 95% confidence interval. Our Z is going to be bigger because we're coming out further. There's more area in the middle. It's 95%, which means Z needs to come out further in either direction. So for 95% being in the middle, that means there's 5% left over. And when I split that for each wing, that means 2.5% in each wing. And as a decimal, that would be 0.025. So if I want to find the Z critical, meaning how far out I come in either direction, how far out I come to make that confidence interval in terms of standard deviations, I need to put in 0.025 here. So as you see, instead of coming out to 1.64, we came out further because there's 95% in the middle now. So 0.025 is for this side, and now we should get the same exact thing, just negative, when I do the left side. So 1.96 standard deviations to come out this way for 95% confidence interval. If I do the left wing, and I put in 0.025, look, it's the same thing, just on the other side. It's negative 1.96. So in order to make my 95% confidence interval, my z-critical, meaning how far I come out in terms of standard deviations, would be 1.96 in each direction. So now let's take a look at example 5. We have what we need to find all the important pieces of information for parts A through D, and then we're going to use that information in part E to plug into our formula and find the sample size that we need. So example 5 reads, researchers want to estimate the average coffee yield per tree in a Colombian plantation. They want the estimate to be within 0.11 kilograms of the true mean, and we have a 96% confidence interval. Previous data showed that the standard deviation is 0.8 kilograms. Identify the following and then use your answers to find the sample size. So this is the picture that we have. We're trying to estimate a mean. So our point estimate is going to be in the center, and that's going to be our sample mean. Okay, the question says we want the estimate to be within 0.11 kilograms. So that's our error. We want to be within 0.11 kilograms. So that's our error. So for part A, we're going to say that our error is 0.11. Now, we want a 96% confidence interval. So that means we want 96% to fall under the graph between the two values for the upper and the lower bound. So this is going to be the lower bound. This is going to be the upper bound, and we want 96% to be shaded in the middle. So we know that what's left over is 4% in total, but when we split that between the two wings, it's going to be 2% in each wing. So here's the picture of what we have so far. So for part B, we know that we want a 96% confidence level. We need to find our z-critical. So that tells us how many standard deviations do I need to come out from the center on either side. So use GeoGebra. Pause the video. You should get, when you do that, 2.05 when you round it to two places. Okay, part D says we need to find the population standard deviation, and that's given to us up here as 0.8 kilograms. So that's 0.8. So the last thing we have to do is find our sample size. And here's our formula. We take our z-critical, we multiply by our standard deviation, and we divide by the error. And then we take all of that and we square it. So we're going to make sure when we do our calculations and your homework, make sure you round your critical value to two places. Because if you don't follow the rounding directions for your critical value, your answer is going to be off. Okay, so our critical value is 2.05. We're going to multiply that by the standard deviation, which is 0.8, divide by the error, which is 0.11, and then we're going to take that whole answer and square it. When we do that, we're going to get 222.2809917. With sample sizes, you always want to round up. If you round down, then you may not have enough in your sample to meet these requirements that you want. So our final answer should be 223. So in order to meet all of this criteria, in order to get a 96% confidence interval with a margin of error of 0.11 and a standard deviation of 0.8, we need to have 223 people in the sample. Okay, let's look at example 6. The Bay Area Rapid Transit System, known as BART, is evaluating interest in a new express line. Officials want the estimated proportion. Here's a key word here. We're not estimating a mean here now. We're estimating a proportion. So we want the estimated proportion of supportive riders to be within, there's our error, 0.041 of the true proportion. Here's another key word to look out for. We want a 97% confidence interval. Okay, so here's the picture. When we're doing proportions, because of the central limit theorem, as long as we have a sample size big enough, we can estimate the binomial distribution for the proportions with the normal distribution. And this is where the central limit theorem is key. But this only works if the sample size is big enough. So let's see. Here's our point estimate. In this case, it's a proportion. So our symbol for a sample proportion is P with the little hat over it. It's called P hat. We want it to be within 0.041. So here's our error. So we want our interval to come out in either direction with an error of 0.041. We want a confidence interval of 97%. So in the middle, we want 97% shaded under the graph. So that means there's 3% left over. So there's 1.5% in each wing. So our error is going to be 0.041. Our confidence level is 97%. If you're asked to write that in on the homework, I believe you need to put it in as a decimal. So make sure you put it in as a decimal. Our critical value, we need to find that. So pause the video and see if you get the same thing I do. I am getting 2.17 for the critical value when we round it to 2 places. Now, for part D, this is asking for a preliminary proportion, and that information is not given in the problem. So for this, it does not exist. I'm going to put in D and E. So now we need to take all of this information and find our sample size. Because we do not have the preliminary proportion, we're going to use Z critical divided by the error squared, and then we're going to multiply by P, which is, we're estimating at 0.5, and Q is 0.5, which is what gives us the 0.25 or the 1/4. So Z critical is 2.17, the error is 0.041. We're going to square that and multiply that by 1/4 or 0.25. We get 700.312,314. And again, we always round up. So the final answer is going to be 701 members need to be in this sample.